Hello, marvelous AP Calculus AB students, and welcome back to day 3. This is our second lesson, lesson 1.2, in our first topic on limits and continuity. We have 2 daily learning objectives for today. The first is you're going to need to be able to graphically interpret and estimate one-sided and two-sided limits. A lot to unpack there, and we'll do that as we move throughout today. Secondly, you're going to need to be able to express graphical limits symbolically using correct notation. And there's less that's new there. We focused a lot on the notation, the 3 parts that you need for a limit last class. So let's go ahead and just jump into a nice bit of review. So our opener for today is to use this graph of f of x, and this is important, and we'll see this a bunch throughout today. This is all one graph. Now you might say, well, isn't there like kind of a curvy piece here and another kind of curvy piece here, and there's this extra weird point here? It looks like there's maybe 3 different graphs here. No, this entire graph is called f of x. Now f of x might be made up of different functions, but it is all one graph. So we are going to be asked questions about the graph of f of x on the left, and we're going to be using the graph on the right to answer. So why don't you guys go ahead and pause this video, try the 8 questions there, and then once you've tried those, unpause and we'll take a peek at the answers. Ready, set, go. All right, you're back. You might have noticed that each of these asked questions in pairs. For example, question 1 asked about the limit as x approaches -4 of f of x. And question 2 asked about f of -4. Now please remember, limits do not talk about what happens at a point. So these odd numbered questions are going to talk about what happens close to the point, versus these even numbered questions are going to be saying what happens exactly at the point. And I think it's nice to pair them this way so we can compare and contrast the differences. So let's look at one. As we approach an x of -4, you might say, well, as we move closer like this, no, we're asking about the function f of x. So we're going to trace along the function f of x until we get x's that are close to -4. For example, this point right here, if you thought about the x value, would be like -4 point, I don't know, maybe 4.2, something like that. That's pretty close to -4, but this is even closer. And so we have -4.2, maybe this is -4.1. We don't particularly care about the x's. We want to know what the y's are. So if we're thinking about this, the y value that's associated here is very close to +2, just underneath +2. And if we did the same thing the other direction, and we looked at a point very close to -4, maybe this is -3.9, the y value here is also very close to +2. So what you'll see often is people will kind of trace here and here and say, what y value are those two approaching? Well, you're approaching below and above to the same spot you're approaching +2. However, that's very contrary to what happens exactly at an x of -4, because exactly at an x of -4, there's no graph at all. This open circle reminder is not a point. That means you trace, you pick up your pencil, and then you continue tracing. That's a gap right there. There is no point at -4. So I'm going to cross off that equals because we only equal a value. And we say f of -4 does not exist. Let's go ahead and move on through. Now the third question asks us the limit as x approaches 1. So we can identify hopefully 1 on the x-axis. And as we trace our graph, we're getting very close to 1, kind of right about here, right? This point is exactly at 1. So we're getting closer and closer to the left side. It looks like we're kind of getting closer and closer to a y value of 4. But as we approach 1 on the right side, right, this is like 1.2, 1.1, really, really close to 1. Looks like we're getting closer to -2. And although there is a point at 1, limits don't talk about what happens at a point. They talk about what happens infinitely close. We discussed last class, though, we saw this in a table. If we get infinitely close to an x value, and the y values approach 2 different points or values, then we actually say that the limit does not exist. So this is a nice graphical example of a limit that doesn't exist. You can see this nice jump in here. It's called a jump discontinuity. Let's go ahead though and see what happens at f of 1. At 1, what is the y value? Well, there aren't 2 points here. You might be tempted to say this is the point 1 comma negative 2 and 1 comma 4, but that's wrong for 2 reasons. First, this would not be a function, and it wouldn't be a function because 1 would have 2 different outputs. We know that's a no-no. It doesn't pass the vertical line test. And 2, there are not 2 different points here. There is no point here at all. This open circle is just to show us that this graph stops infinitely short of the point 1, negative 2. The only point here is the point 1 comma 4. So a couple to go. As we approach positive 4, see, where's 4? You might say, oh, well, we can't do that. There's no point here. Well, of course there is. Remember, graphs are made up of an infinite number of points, right? We don't put them all because that would be very tedious, but any part on the graph is a point. So if we look at 4 and we go down and we look at this, this is the point 4 comma negative 2. All right, so let's check the limit first. As we get infinitely close to 4 on both sides, it looks like we're getting closer and closer to a y value of negative 2. And directly at 4, there is a point at negative 2. The limit and the point are equal here. Let's do one more as we approach 6 this time. So as we approach 6 from the left and from the right, not at the point, but as we get very, very close to the point, it looks like we're sitting at a y value of 5. However, directly at 6, where is the point located? The point is at 2. All right. Now, this focus for today is about graphical limits, finding the limits from a graph. But what if you're not given a graph, right? Last class we were given tables, or sometimes we made tables. This class we have an equation, but since we're focusing on graphs, what do you think we'll have to do? Oh yeah, we're going to have to create the graph and then find the limits, right? There are going to be some shortcuts that we'll learn later on about how to find limits from equations, but that's going to kind of be the end of our limits focus. For now, we're just talking about graphs. So the first thing we're going to have you do is take this piecewise function, right? Piecewise because there's 2 different pieces to it, and graph the full function, right? It's going to be a graph something like this. All right, definitely not the same shape, but it will have multiple pieces. So let's see what you can do. Ready, set, go. Now, there are a few ways to graph a piecewise function, but the most basic, and that's what I'll share with you for now, is to just graph each piece or each branch of the piecewise function separately and then erase. So you might want to do this lightly and have your eraser ready to go. We're going to start with this top branch, which is the equation y equals 2x minus 4. Now, at the end of this, we aren't going to have the full graph of 2x minus 4. We're only going to have a piece of it. But let's make sure we remember how to graph. We start at negative 4, up 2 over 1, up 2 over 1, nothing too bad. And then you can absolutely connect these with a nice line, like so. Then we need to graph the other part of the equation, y equals negative 2, which is a y-intercept of negative 2, and it's that nice horizontal line. Okay, now clearly this is not a function, right? It's not a function here or here or here. We see that we're failing the vertical line test over and over again. This piecewise function is going to remove certain pieces of these graphs, so it is a function. And let's go ahead and start with the green function I have up here. It says we want the diagonal line 2x minus 4 for all x's except x equal 3. That's why it says if x is not equal to 3, make this line. So let's go ahead and take a look at x equals 3. Here's 3, and there's a point. We only want this green function for x's not equal to 3. So what we're going to do is we're actually going to take away x equals 3. And we do that by doing a nice open circle and then reconnecting. This is the equation y equals 2x minus 4 for x's not equal to 3. Then we look to the red one, and it says we want the horizontal line y equals negative 2 only if x equals 3. So at x equals 3, we want that point, but we don't want any other part of this equation there. So this is the piecewise function with 2x minus 4 for x is not equal to 3 and negative 2 if x is equal to 3. All right, we've done it. We have graphed this function f of x. Let's go ahead and answer a few questions about it. First, the limit as x approaches 0. So let's see, 0, this is an x of 0. As we approach 0, we get closer to what value on each side? Looks like negative 4, huh? And then what happens exactly at 0? Well, there's a point, negative 4. All right, now the most common question asked about piecewise functions is where the piecewise function changes. And clearly the piecewise function is going to change at 3. So the first question is the limit as x approaches 3. So as we get closer and closer to each side, it looks like we approach a y value of 2. However, at f of 3, exactly at 3, we have the point with a y value of negative 2. Right, we're feeling okay here. We're maybe hopefully doing a better job of understanding the difference between a limit and a point, and as a nice bonus, what piecewise functions look like and how they're graphed. All right, now our daily objective today talked about graphically determining limits from one-sided and two-sided limits. Now we just spent time on a two-sided limit or multiple two-sided limits, where we looked at what happened as we got closer to a point from both sides at the same time. However, one-sided limits are going to be a little bit more powerful, and I think logically you're going to understand exactly what a one-sided limit is, but let's run through some background. Although we know that a limit does not exist if an equation or a graph or a table does not approach the same value on both sides of the x-coordinate, right? And we saw that one back up here. We approached two different values, so we said the limit did not exist. Okay, we can still learn a little information from just looking at a piece of a limit. So instead of looking at both sides of an x value simultaneously, we look at each side of the x individually. This concept is known as evaluating one-sided limits. Because there are two sides to every point, we look at the left side or the negative side of a point, and the right side or the positive side of the point separately. And they're notated like this. A left hand or a left-sided limit says the limit as x approaches a, and here's this little negative, from the left or negative side of f of x equals something. And this other one says the limit as x approaches a from the right or positive side. So let's put this into practice. We have a very hopefully familiar graph. We looked at this one on the previous page, and we're just asked about 6 limits here. So never at the point, just close to the point. And we'll try one together and then give you some time to try the rest on your own. This says the limit as x approaches negative 4 from the left or negative side of f of x. So here is the x value, negative 4. If you think about the x-axis, we have a right side and a left side. If you think about a point, we also have a right side and a left side. When we ask about what happens as x approaches negative 4 from the left side, what they really mean is as we get closer and closer to this point, just on the left side, right, this is the left, on the left side of negative 4. And we are approaching a y value of 2. Now, as we approach negative 4 from the right side, we are also approaching a y value of 2. So go ahead and pause me, try those last 4, and then we can quickly share out answers and move on. Good luck. All right, hopefully you guys found success. Really the only strange ones are going to be 3 and 4 here, so we should probably look at those right now. Problem 3 asks us as we approach 1 from the left side, and I feel like from the left side we're getting closer to positive 4. And then from the right side, well, now we're down here getting closer and closer to 1. From the right side, we get closer to negative 2. This last part, as we approach 6 from the left side, we get closer to positive 5. That's hiding up here. And as we approach 6 from the right or from the positive side, we also approach 5. Now, you might notice something here where our one-sided limits approached the same value then on the previous page, you'll notice that that limit had a particular value. However, where our limits approached two different one-sided values, our limit ended up not existing. Which makes sense because we've said in the past that a limit only exists if you approach the same value on both sides. But now we have a way to symbolically say this instead of just saying it in words. The limit as x approaches a of f of x equals a specific value, IFF. This IFF right here, if you wanted to take notes on it, means if and only if. Okay? If and only if. And what that means is that you can actually read this theorem forwards and backwards. And we're going to explain that in a second too, but let's just read it forwards to start. The limit as x approaches a of f of x equals a value, if and only if the limit as x approaches a from the left side of f of x equals that value, and the limit as x approaches a from the right side of f of x equals the same value. Or if you read it backwards, it tells you if the left-hand limit and the right-hand limit equal the same value, then the overall, the two-sided limit exists. All right, so let's go ahead and try and use that definition to justify why a limit does or does not exist. Example 2. Use the graph given below to answer each of the following questions. The limit as x approaches 5 of f of x does not exist because. All right, well, if we look at this, we can certainly see from the left side we are somewhere, and from the right side we are somewhere else. That's not mathematically rigorous enough. We can't tell someone on the AP exam, oh, when I drew arrows, we approached two different spots. They want you to be able to mathematically explain. And so we do that using one-sided limits. We're going to find each one-sided limit at x equals 5, or as x approaches 5. So we're going to find the limit as x approaches 5 from the left side of f of x. And when we do that, we get closer and closer on the left side. We approach the y value of 2. Okay? And we're going to find the limit as x approaches 5 from the right side of f of x. And as we approach on the right side, we approach the y value of 4. All right. What does that tell us? Well, our one-sided limits equal two different values. So we can say, therefore, this triangle right here is a very common symbol to say therefore, so we don't have to write it out. Therefore, the limit as x approaches 5 of f of x does not exist. All right, we don't put that equals because does not exist isn't a value. And there we go. So if you're ever asked to prove why a limit doesn't exist, this is what they're looking for. You need to go back to the one-sided limits and show that they are two different values. Now part B on here brings in our one-sided limit practice, but it also brings in something we maybe haven't seen before. Now they're asking us to add two limit values together. And we did something kind of like this with our table, but let's see if we can determine the answer here. The limit as x approaches 3 of f of x, well here's 3. As we approach 3, I think we are approaching the same value. We're approaching 1. So that is 1 plus. And then the limit as x approaches 5 from the left side. Well, the left side is this side, and that is 2. Now notice that the overall limit doesn't exist, but that's not what we're asked about here. We're just asked about what happens as we approach 5 from the left side. So this scary looking sum of limits is actually just 1 plus 2, and so it has a total of 3. Nothing too terrible. All right, moving on. The last thing we're really going to practice doing today, even though there's a few other new things here, this is the last really big graphical piece of today, is you should be comfortable sketching a graph where they give you specific information about the graph, and then you can use your imagination to expand on that information and make an overall function. So let's take a look. Sketch a possible graph for a function f where the limit as you approach 1 from the right side of f of x is -1, from the left side is +1, and f of 1 equals -1. I always like to start with the points. I think those are probably the easiest. This is 1, comma, negative 1. We took care of it. Then we have two different limits here. So we can start with the right side. As we approach 1 from the right side, my y values better be approaching negative 1. So they didn't give us any other information about the right side, but we know that whatever's happening over here has to be approaching negative 1. Took care of that. And then they tell us from the left side, we better be approaching positive 1. So whatever's going on over here, from the left side, we better be approaching positive 1. But how do we show we're approaching positive, whoops, I didn't even get to positive 1. Positive 1's up here. How do we show we're approaching positive 1 and not, let's say, oh, I don't know, like positive 1.2? Well, that's where our open circle comes in handy. There's no point here, right? Limits don't talk about what happens at the point. We already have a point. We just need to show that we're approaching an open circle, which is clearly showing a y value of 1. Now, this is kind of a weird function, and I made strange little curves here. You didn't have to have curves, but I'm going to finish this one off. Right? Our function can do anything we want for the rest. Right? We were only given 3 pieces of information. We took care of those 3 pieces of information. Doesn't matter for the rest. Now, you could have made a very boring function if you wanted. You could have just had it go like this and like that. That's fine too. Or again, you can let your imagination run wild and you can throw some squiggles and some waves in there. Nothing too terrible. All right. Now we're going to sketch a graph of a function f where these couple things happen. Let's start with the point again. F of 2 is negative 2. Easy. And then we have a couple limits. As we approach positive 2, the y values get closer to 3. So here's positive 2, and the y values are getting closer to 3. Now, the limits don't talk about what happens at a point, so we'll put an open circle. We're going to say that we are getting closer to 3 on each side. So our graph goes over here, jumps down to the point, continues up over here. Nice. Both sides, because they didn't just give us a one-sided limit. Then the limit as x approaches negative 1 of f of x equals infinity. We haven't seen one of these infinities before. How does that work? Well, we have negative 1 over here, and they're telling us from both sides the y values are infinitely large. Here's our y-axis. Where's infinitely large on the y-axis? Oh, that's way up here. Here's infinitely large. So we can kind of keep this point up here just as a reference. We're trying to tell people that my y values over here and over here, right, on either side of negative 1, better be getting infinitely large. So I think this guy is going to have to go up and up and up. And this one over here, whatever it's doing, also has to go up and up and up. Right? We never quite reached that. We can't put an open circle in the middle because then that would be a specific number. These are just going up, up, up. In fact, I think in the past we've probably called that a vertical asymptote. Right? We can see that my graph is going infinitely tall. We're going to have more on that in the next few classes, but I thought it was a nice one to throw into you now. And that's about it. So we have a couple practice problems here. Why don't you try these two and then unpause me and we'll get to the last part of today. Ready, set, go. All right. Well, this one says a continuous function satisfies the following 2 conditions. I think there's probably a typo there, but let's see what we can do. So they told us that f of 1 cannot be 3. So whatever it is, f of 1 cannot be 3. There can't be a point there. But they did tell us that the limit as x approaches 1 of f of x is 3. So what's happening is as we get closer and closer to 1, our y values are getting closer and closer to 3. So I think this x actually has to turn into an open circle. And then f of 1 can't be 3, but it could be anything else, right? So I don't know, maybe we put it down here and we say, ha, it's negative 3. Yeah, you can put that point anywhere you would like, and here's our function. Now I said a continuous function probably isn't accurate because as you sketch this, a continuous function will require you to never pick up your pen or pencil. But to do this graph, we'd get all the way over to 1, then you'd have to pick up your pencil, put it down at negative 3, pick it up again, and then follow the rest of the graph. So I think continuous doesn't work. But other than that, can you see how everyone in your group could have a different graph? Right? You wouldn't have to put the point here. It could go anywhere. The outsides of your function could look different. Nothing terrible. Okay, let's look at our last one. We need to find f of 3 first. F of 3, closed circle, that's 4. We need to find the limit as we approach 3 from the left side. That's 2. We need to find the limit as we approach 3 from the right side. That looks like 6. And then we need to find the limit as x approaches 3 of f of x. And so as we approach from both sides, we're in two different spots. I'm going to say this limit does not exist. But wait, it says if any value does not exist, justify your answer with one-sided limits. Why doesn't that exist? Well, we actually already said it over here, right? The limit as x approaches 3 from the left side of f of x, we already stated that value, is not equal to the limit as x approaches 3 from the right side of f of x. If we've stated a value for something earlier, we don't need to write it again. So I just explained that the two one-sided limits aren't equal, which automatically means our limit doesn't exist. All right, last page. Now, as we move through, especially to tomorrow, we're going to start finding limits without creating a graph or a table. Many of you are like, phew, that's way better. On one hand, it is a little less work, but on another hand, you're going to start to make some mistakes just because equations tend to be a little trickier. Graphs and tables are much more easily seen in terms of a limit. However, we're going to start expanding or stating our limit laws that apply to graphs, and we'll talk about that, but also to equations so that you've seen them ahead of next class. So technically, there are many limit laws that we follow when we evaluate limits. Okay, if we look at them written down, f of x and g of x are going to be standing in for two functions. You could even think of f of x and g of x standing in for two graphs, right? Maybe f of x is this graph and g of x is this graph over here. Okay, and last but not least, c is a constant. When we say something is a constant, we say that's just a specific value that doesn't change. Maybe c could be 7. We're going to go ahead and read each of the 6 laws and then name them in any name or any explanation that you would like to use, because I found that when students create their own names for these limit laws, they tend to remember them a little bit more. Okay, so for example, if you have the limit as x approaches a of one function plus another, it's totally okay to find the limit as x approaches a of one function, the limit as x approaches a of the other function, then add them together. So what could an easy name for this be? You could say it's something like the limit summation law. I've had students say it's the adding limit law. Whatever sounds good to you. Now don't forget that graphically this is actually pretty interesting. What it's saying is if you had the graph of something like x squared and 2x, so we would be looking at the function x squared plus 2x, which is a parabola that's shifted a little bit. They're saying that instead of finding the limit of that one graph, you could break it into two different graphs. You could look at the graph of x squared, just a parabola, and the graph of 2x, which is just a line. Find the limit of each one of those and then add the results together. So instead of it all together, you're allowed to split it apart. All right, so why don't you read through the rest of these, see what you can do, and then we will come back together and discuss a couple idiosyncrasies or weirdnesses for these limit laws. Ready, set, go. All right, and we're back. So these limit summation, and this one you could say like subtraction laws, aren't too terrible. I think you're pretty comfortable with those. The third one down here tells you if you have a constant in front of an equation, you can factor that constant out, right? So for example, if you had something, and I'll give it up here, if you had something like the limit as x approaches 3 of 5x squared, instead of considering the graph 5x squared, you could actually factor the 5 out and just find the limit as x approaches 3 of x squared, which is nice. It's smaller numbers and then just multiply by 5. Okay. Now our fourth one though is different. Instead of a constant, a single number times an equation, our fourth one has two equations multiplying together. So those equations could be something like x squared and cosine of x, right? And they said that you can actually find the limits completely separately. Now there is a caveat or an exception here that only works, in fact all of these laws only work as long as both limits exist, right? So for this right side, I'm just going to say something like both limits must exist. And I'll do a bonus video on what I mean by that at the end of this unit. One or two questions over the last like 60 years of AP Calculus might have asked about this. It's not super common, but long story short, if both limits don't exist, you're not allowed to split them apart, and there's some other do more methods that we might discuss. But either way, this just says if you have them separate, or you have two functions multiplying, you can treat them separately and find the limits there. Our fifth one says if you have two functions dividing, find the limit of each one separately. However, the bottom limit can't be 0, and I bet you could probably see why, right? If this bottom limit down here was 0, then you'd be dividing by 0, and we would say does not exist. And last but not least, if you have a function to a power, you can just find the limit of the function and then do the answer to that power. So let's actually go ahead and practice that over here. So given the following properties, evaluate the limits first by splitting the limit into its individual components. Don't forget that perfect notation. Okay, so here they've given us 3 values, what happens at a point, and 3 limits, what happens close to the point. Okay, so if we look at problem 1, what I'm going to do first is I'm going to split this. I'm going to try and keep the limit as long as I can. I see division here. So I'm going to go ahead and split this using my division rule up above. And you might want to write kind of small here. We're going to find the limit as x approaches 3 of f of x cubed. And then I'm going to find the limit as x approaches 3 of 5 times g of x. Now we still have a couple issues here because none of these show f of x cubed, and my screen did that fun thing where it just disappears again. There we go. And none of them showed the limit as we do 5 times g of x. So I haven't broken this down enough. Instead, I'm going to go through here and I'm going to say, oh, well, I'm actually, based on the law up above, allowed to just find the limit as x approaches 3 of f of x, and then once I'm done with that, I can cube my answer. And then same thing down below. There's this 5 here, so I'm going to go through and say, well, I'm allowed to factor this 5 out, and then we're just going to find the limit as x approaches 3 of g of x. So we've now broken this down into smaller pieces of which I know the answer. Now be careful here, right? I don't want to do the limit as x approaches 3. Maybe it's when I zoom out too far. No. We don't want to go through and say, oh, the limit is x approaches 3 of f of x. Well, f of 3 is 3, so the answer is 3. We're still talking about limits here. We need to use this second column. So the limit as x approaches 3 of f of x is 2. Don't forget that there's still a cube. And the limit as x approaches 3 of g of x is 8. Now notice, once I found the answer to this whole limit, I replaced it, right? We know when you see something equal to something else, you can do a replacement. So I replaced the entirety of the limit as x approaches 3 of f of x with 2, and same thing with 8. Now we should probably simplify this a bit, right? So as we go through to simplify, I just decided to close everything, very exciting. We end up with 8 over 5 times 8. Our 8's cancel, and we end up with a placeholder 1 on top and a 5 on the bottom, 1/5. Okay. So let's go ahead and try this second one. Now that you know what you're trying to do, you're trying to break them down so that you get these individual statements that you can evaluate. Okay, so try problem 2, then we're coming back together. Ready, set, go. All right. Hopefully we had some success here. Again, it can be a little bit tricky, so let's take a look. We're going to find, let's move to the right. No, we're going to stay here. The first thing I'm going to do is I'm going to say, oh, we have h of x that's multiplying by this monstrosity, so let's make 2 separate multiplication limits. That's one of our laws up above. We can find the limit as x approaches 3 of h of x, and then we can find the limit as x approaches 3 of 2 times f of x plus 3 times g of x. I should probably put that in parentheses. There we go. But I think we can actually go even further here, right? We can go even further by saying, let's do the limit as x approaches 3 of h of x, and then we'll break this guy down into two smaller limits. There's a 2 that I can factor out, and then just find the limit as x approaches 3 of f of x. But then there's a 3 I can factor out, and we can just find the limit as x approaches 3 of g of x. Right? So we had two separate functions that we split apart, and that is like our very first limit at the top, the summation of limits. And then we had constants that we're also allowed to factor out. So to me, this looks like we can now find the limit as x approaches 3 of h of x, which is 2, and, keeping my parentheses, 2 times the limit as x approaches 3, which is 2, plus 3 times the limit as x approaches 3 of g of x, which is 8. So I went through and replaced the limit for h of x, the limit for f of x, and the limit for g of x. And now we go through and start to simplify. The inside is 4 plus 24, it's 28, and 2 times 28 looks like 56. Nothing too bad, just using those limit laws above to break everything down. All right, last problem for the day. We're going back to our graphical limits. The graphs of the functions f and g are shown below. Find the value of the limit. Okay, well, if you wanted, you could try and make a graph of f of x minus 3 over g of x squared. But let's see if we can break this down into smaller pieces. Right? One piece we can certainly do is the limit as x approaches 4 of f of x minus 3, and divide that by the limit as x approaches 4 of g of x squared. Now these are the graphs of f and g, and we still have an extra minus 3 and a square, so I think we can go even further. The limit as x approaches 4 of f of x minus the limit as x approaches 4 of 3. Right? We split this into two different limits, and then we can divide this by the limit as x approaches 4 of g of x, whatever that is, we square it. So finishing this off, the limit as x approaches 4 of f of x. Well, as we get closer to 4 on both sides, we don't want to talk about the point. Limits talk about what happens close to the point. That looks like 3 right there. Okay. And then the limit as x approaches 4 of just plain old 3. How do we do that? Well, let's make a quick graph, right? Just a real small sketch of one. They are asking us about the function 3. So what does the graph of y equals 3 look like? 1, 2, 3. It's a horizontal line, just like so. And they're asking us what happens as we get close to an x value of 4. Well, as we get close to 4 on both sides, doesn't the y value just approach 3? And so this limit here, the limit as x approaches 4 of 3, is just the value 3. All right, denominator, the limit as x approaches 4 of g of x. Well, as we approach 4 on both sides, it looks like we get 5. And then don't forget that there's still a square. 3 minus 3 is 0 over 25. 0 divided by anything, we know, is 0. So a quick recap of what we accomplished for today. Let's start with those daily objectives. First, we wanted to make sure we could graphically interpret and estimate one-sided and two-sided limits. So we opened with two-sided, we did a bunch with one-sided. Then we wanted to make sure we could express these graphical limits symbolically using correct notation. Can we use that one-sided and two-sided limits? Can we realize that we don't equal does not exist, we just say it does not exist? We talked about graphing piecewise functions, one-sided limits, creating our own graphs, finding limits from graphs and justifying why a limit doesn't exist, and last but not least, a few limit laws where we did a couple examples when we were given values either from a table or from a graph. So hopefully you found today useful and nothing too terrible. Next class, we're going to jump into our limits algebraically, which means without making a graph or a table, how can we find a limit from an equation? Have a great day.